Okay, welcome to a set of notes where we're going to talk about different models of the atom, and we're also going to talk about something called atomic spectra, which helps us identify what types of atoms we have. Okay, so we spent our first video was on wave-particle duality, the idea that light has both wave-like and particle-like properties. Now we're going to talk about the atom in particular. There have been tons and tons of people throughout history who have tried to predict how atoms are structured. They're so small that we can't really observe them with normal technologies. We're just getting to the point now where we can kind of do that. But people have always theorized, if you take matter and you divide it down to smaller and smaller blocks, what do you get at the end? What is truly indivisible? The first person that I know of, at least, to conceive the idea of atoms, some fundamental building block to the universe, was a guy in ancient Greece called Democritus. He lived, like I said, in ancient Greece around 400 BC. Matter of fact, our word atom actually comes from a Greek word which means indivisible. The Greeks, however, they're technologically limited, and they didn't do too much experimenting. They were just more philosophers than anything. Fast forward about more than 2,000 years, and we get J.J. Thomson. J.J. Thomson is a British guy, and through his experiments, he discovered that electrons were very low mass, they had tiny masses, and they were negative. Now, it was known at this time that atoms, which are the building blocks of the elements, obviously electrons are subatomic, subatom particles. They're inside the atom. Atoms were known to be neutral. Okay, the building blocks of the elements were known to be neutral. So therefore, if electrons had negative charge, in order for the atom itself to be neutral, there had to be some sort of positive charge in there as well. And Thomson's idea, where he thought that electrons were embedded inside the atom. He kind of thought that they were embedded in what he referred to as kind of like a positive goo or soup that was spread throughout the atom. And the name, so it kind of looked like this. Okay, here is the electrons. I'm going to symbolize them with E's. They're just kind of spread throughout this kind of amorphous blob here that was positive. Positive goo. And the phrase you always hear with this one is raisins and plum pudding. I guess plum pudding is some sort of like British dessert, some sort of meal, where in this model, the raisins would be the small little electrons that are negatively charged. The plum pudding is what the raisins are surrounded by, and that has a generic positive charge to it. What I like to think of, because we don't really have plum pudding here, is when you go and buy yogurt from, let's say, the supermarket, and it's got the little chunks of fruit in it. Imagine Thomson's model was that the chunks of fruit were the electrons, and the yogurt part was the what was the positive, the spread out positive charge. So first model, I guess it kind of makes sense, Thomson's model, but the nice thing about models is you should be able to test them. So along comes this guy, Ernest Rutherford. He is famous for the gold foil experiment, which you talked about in chemistry. Rutherford, I believe, is from New Zealand. What he did was he took the nuclei of helium atoms, so positive helium nuclei, and he shot them at very, very thin gold foil, this very, very thin sheet of gold atoms. By the way, a positive helium nuclei has another name. It is known as an alpha particle. If you think about helium, it's the second element on the periodic table. That means it has 2 protons in its nucleus. It has 2 protons and 2 electrons. So basically what he was doing was he was shooting alpha particles, which contain 2 protons and 2 neutrons, at this gold foil. And we were going to see what happens. If Thomson was right, if the plum pudding model was right, then because the positive helium nuclei, they have a positive charge. The goo has a positive charge as well, but it's very spread out positive charge. Basically, it shouldn't do anything to stop the alpha particles. If Thomson was right, then these alpha particles should shoot straight through. Okay? When he shoots the particles at the goo, they should pass through, no problem. And this is why you always do an experiment more than once, okay? You always get as much data as possible, because most of the time, the positive particles, the alpha particles, did shoot straight through. Most of the time they did. But a very small number actually bounced straight back. Some were scattered off at weird angles, but a small number actually bounced straight back. They came right back at what he was shooting the nuclei with. You can think of it as your alpha particle gun. they bounce straight back. And the only explanation for this, the only reason that they would come straight back, is that they were repelled by some small, or no, I shouldn't say small, but some very dense positive charge. Okay? The spread out positive charge wouldn't do this. The only thing that would do this if there's a very small, very dense positive charge, that if the alpha particle happened to be right in line with it, it would cause it to stop, since we know positive charges repel each other, and go back the way it came. It was reasoned that because this happens, basically what was happening was that in the cases where it went right through, it was the alpha particle wasn't coming near this dense positive charge. But when it did get bounced back, it just happened to be right on target with it. So the idea became that there must be a very small positive nucleus in the center with electrons in orbit around it. So there has to be a small, dense positive charge. Rutherford theorized that this was located right in the middle of the atom. And if that's in the middle, the electrons, which have negative charge, are going to be attracted to it, so maybe they're in orbit around the nucleus. Now, this looks very similar to the picture that you all have in your head. Okay, seems like it works. But here's the problem. Rutherford didn't say that there had to be any sort of set orbits. In this problem, or in this theory, it was found that the orbits would end up being unstable, and therefore the electrons would decay toward the nucleus, and you'd end up with electrons in your nucleus. And we knew that we didn't have that. We didn't have electrons in the center. They were out on the outside. There were no electrons in the center. Think about it. If the electrons were in the center, wouldn't they have attracted those helium nuclei? We didn't see that. Okay? So the issue with the electron orbits was, in this model, they seemed to be unstable. They would decay towards the nucleus. And the reason that they were unstable is because electrons, if they're in orbit, if they're moving in circles around the nucleus, they should continuously emit light. Remember, the way we get electromagnetic radiation is we take a charge and we accelerate it. And if an electron is in circular motion, then it has some centripetal acceleration, it should be producing light. We don't see that. That's why the electron would decay down. But that's not happening, so something else must be going on, okay? We've got the idea here. We're starting to get the ideas. It's a small positive charge in the nucleus, but the model isn't quite right. So along comes Niels Bohr. I believe he's from Denmark. He took quantum theory from his buddy Max Planck. Remember, quantum theory was the idea that electrons can only gain or lose energy in fixed amounts called photons. This was the idea behind the particle nature of light. Okay, light can be considered to come in little light packets called photons. Well, he took this idea that light only comes in certain fixed amounts, and he applied it to the atom. And the rest of the theory goes like this. Rutherford didn't restrain the electrons to have certain orbits. He said they can orbit at any distance. This didn't end up working. Bohr said that electrons can have only certain fixed orbits. So they have to orbit a certain distance out from the nucleus. And the electrons are not trapped in those orbits permanently. They're in the orbits, but they can go up to higher ones or down to lower ones. They can go up to higher orbits farther away from the nucleus. More. So if they go up to higher ones, farther away from the nucleus, those are more energetic energy levels. By absorbing a photon. You learned this last year in chemistry. If an electron absorbs a photon, it goes to a higher energy level. And you also learned the reverse. If electrons fall down to a lower energy level, they emit photons. And as it emits a photon, it's emitting some light. Based on how much energy it's giving off, this appears as different types of light. It might appear as blue light, it might appear as red light, it might appear as infrared or X-ray or radio waves. But basically, however much energy is given off determines the type of light that's released. In Bohr's theory, the lowest orbit that an electron can have, the lowest stable orbit, is known as the ground state. And right now we're going to take a look at the reference tables real quick and just see where we're getting ground state from. We're going to go to page 3 of the reference tables, and we have some energy level diagrams. We have energy level diagrams for hydrogen. We have energy level diagrams for mercury. Notice that the ground state is at the bottom of both. For hydrogen, ground state is called N equals 1. For mercury, ground state is called A. Why is one of them N equals 1? Why is one of them A? I don't know. I'm not particularly interested. Higher orbits are known as excited states. So we have ground state, which is the lowest, the closest orbit to the nucleus. Then we have excited states as you go farther away. The excited states are given as follows: N equals 2, or 3, or 4, etc., or B, C, D, etc., depending on which type of atom you're looking at. Now, we only have hydrogen and mercury. Those just happen to be the two good examples, okay? Hydrogen, N equals 1, 2, 3, 4, 5, 6, up to infinity. And then mercury, A, B, C, D, E, F, G, H, I, J. And there's probably more of them too, but we only show those. Now, electrons didn't have to stay with their parent atom forever. If enough energy is given to an electron, it will escape. It will leave that atom behind. This is your ionization. And basically the rules for all of this, what the ground states are, what the excited states are, how much energy it takes to ionize, are depicted in these pictures called energy level diagrams, showing the energy levels for each atom. So each element has its own energy level diagram. Obviously these are not the same. That's what Bohr thought. He thought we could describe it like this. Bohr's theory was really successful for hydrogen. It almost got hydrogen perfect. It was not good for predicting energy levels of other elements, but the fact that it was so good at predicting hydrogen led us to believe, okay, we're definitely on to something here. We definitely know what we're doing, but there's some things that we're leaving out. So Bohr was about, I don't know, probably about 100 years ago at this point. Within the last 50 or 60 years, maybe even a little bit earlier than that, we have developed a new model called the cloud model, which is an improvement on the Bohr model of the atom. It's the best, most current model, and the feature of the cloud model, the main part that makes it different, is that the electrons are not in fixed orbits. Bohr had the electron the electron has to be in this orbit or it has to be in this orbit. In reality, the electrons have a probability of being in a certain location. Okay, there's a chance that an electron might be here. There's another chance that it might be here, and another chance that it might be somewhere else. This probability is, as you might say, it's smeared out over regions in the atom, kind of like a cloud. Okay, so instead of drawing electron orbits as these like solid lines, this is exactly where the electron is. Imagine if you took that line and you just kind of smeared it. Okay, the electron might be, it has most probably here, but it could also be over here. It could also be over here. Starts to look more like a cloud. If you've ever flown, you've gotten up close to the clouds, you've seen that clouds don't have defined edges. There's kind of hazy beginnings and endings to the clouds. Okay, it's not very well defined. That's why it's called the cloud model. So because you can't quite ever say exactly where a particle is, or predict exactly where it is, that doesn't sound like a particle to me, okay? If you're trying to predict exactly where an electron is, but you can't do it, that kind of is a clue that the electron, well, it's not really behaving like a particle. It's more behaving like a wave. Waves are spread out. They don't really have a location. So this is another clue that an electron isn't really just a particle, but it also has properties of a wave, as we discussed last time. Everything in our universe has both wave and particle properties. In any case, this is the most current model. The Bohr model works pretty good for a lot of stuff, but the cloud model is our best model. All right. Let's talk a little bit more about energy level diagrams, and specifically atomic spectra. So, in your reference tables, as we've seen, there are two different energy level diagrams. you have one for hydrogen, and you have one for mercury. They represent, these diagrams, these are the exact same diagrams in your reference tables, they represent the different amounts of energy that an electron can have as it goes around the nucleus of the particular atom. Each element has a unique set of these energy levels. So you see, here's for hydrogen, here's the ground state, n equals 2, n equals 3, 4, 5, 6, and then infinity. And then we have, for mercury, A, B, C, D, E, F, G, H, I, J. So these are some of the energy levels for mercury. There's probably more, but we just showed you the basics here. So you'll notice that there's energy, so there's the name of the level here, and then there's amounts of energy given over on the right-hand side. The energy levels correspond to how much energy a particle has in that location or in that level. What we're focused on is not necessarily these numbers, but how to get an electron to go from one energy level to the next. To make an electron move up from one energy level to the next one, it has to absorb a photon. Remember, absorb a photon, go up an energy level, in order to increase its energy, to go up to the next energy level. And here's the most important part. The photon that it absorbs has to have the exact right amount of energy to move up, or else nothing will happen. Okay? Remember, photons carry energy with them. So if a photon interacts with an electron, it could give that electron its energy. Let's say you have a photon in the ground state, or an electron in the ground state, and it wants to move up. In order for it to move up, it has to absorb a photon that has an energy equal to the exact difference between where the electron is now and one of these energy levels. So for instance, if you're trying to move as an electron from n equals 1 to n equals 2, what's the difference between negative 13.6 and negative 3.4? So let's do 3.4 minus a negative 13.6, 10.2. And these are units of electron volts, notice. So what that means is the electron that gets absorbed has to have, the photon that gets absorbed by an electron in the ground state, if it doesn't have an energy, that photon, of 10.2 electron volts, nothing will happen. If it's only 9 electron volts, it won't make it up to n equals 2. There are no stable orbits in between n equals 1 and n equals 2. It won't go like halfway up and then fall back down. It just won't absorb at all. Also, if it was like 10.4, there's no stable orbits between n equals 2 and n equals 3. So it won't like go halfway up and then fall back down to n equals 2. It won't move at all. The energy of the photon that gets absorbed has to be exactly equal to the difference between energy levels for that electron to move. That's just how it is. You might be curious about why all these energies are negative. Okay? When an electron is in orbit around an atom, we say that it has negative energy. And all this means is it reflects the fact that the electron is bound to the atom. It can't just go flying off. It is bound by the electrostatic force to that atom. Okay? It's in orbit around it. In order to get farther away, it would need to get some energy. That's why we say when it gains energy, it moves up an energy level away from the nucleus. The nucleus is like down here. It's not completely free to move because it has to stay close to the nucleus due to the fact that the electron is negatively charged, the nucleus is positively charged. However, you can give an electron enough energy to make its energy either 0 or even positive. If that happens, then that's what ionization is. When we talk about things ionizing, what we're talking about is giving an electron enough energy so that its total energy is 0 or positive, not negative like it is when it's on one of these energy levels. When it ionizes, it leaves the atom. So for the hydrogen, if an electron is in the ground state, negative 13.6 eV is the energy level. If you give it positive 13.6 EVs of energy, you make the energy of that electron 0. That's the minimum for ionization. If you give it any more, then that electron will not only leave the atom, it'll also have some kinetic energy left over as it leaves. So any leftover energy becomes kinetic energy. Okay? So electrons that absorb energy, they have to absorb the exact amount to go up an energy level, the exact difference in energy levels to go up to that next energy level. If you make it so that an electron has 0 or positive energy, it will ionize. On the other hand, when an atom returns to a lower energy state, it gives off energy in the form of a photon, in the form of a light wave. Okay, remember, photons are just light particles. We could say that it gives off photons or light particles or light waves. Doesn't really matter at this stage. Okay, when it gives off that photon has a certain energy and a certain frequency. The energy that it gives off, or to determine the energy of the photon that gives off, you find the difference in energy between the initial and final energy levels. So in other words, if an electron falls from, let's say, the C energy level in Mercury to the B energy level in Mercury, it's going to give off a photon with an energy equal to the difference between these two energy levels. Let's see, that looks like about 0.22 electron volts. The equation you use to figure out the emitted energy of that photon is as follows. E photon equals EI minus EF. Notice that it's initial minus final. This is the only time all year that we're going to have initial minus final as the focus. Okay, initial minus final will tell us the energy of the photon that is emitted. The reason you do initial minus final, if it's being emitted, is we know we're going down energy levels. So you do a negative number minus a more negative number, you end up with a positive. To find the energy of an absorbed photon, like for instance, let's say an electron goes from n equals 2 up to n equals 5. You look at the energy levels for n equals 2 and n equals 5, and you use this equation. This time you use E final minus E initial to ensure, again, that it will be positive. And notice some of these are very close together. You got to read very carefully. What they actually do to help is they have little lines pointing down for like n equals 3, n equals 4, n equals 5, and then n equals 6. There's a little line that points up. So just make sure you're reading those very carefully. All right, these equations will be important, and they are in the reference tables. Well, actually, the emitted photon energy is in the reference tables. Okay, the equation, and I just want you to know, this equation right here, EI minus EF equals E photon, that is for emitted photons, photons that are emitted when an electron goes from one energy level to a lower one. If you're looking for the energy of a photon that will cause an electron to rise in energy level, you do EF minus EI. All right, just a few more bits here, and then we'll get to some examples. Once we have the... All right, hold on. Oh, I've got everything flying around here. Okay. Once we have the energy of the photon that has been released, or emitted, or absorbed, or whatever, we can use this equation, which we looked at earlier. I think we looked at this earlier. Energy of the photon equals HF, which is the same as HC over lambda. I think it was actually the last video. We can use this equation once we know the energy of the emitted or absorbed photon to figure out what the frequency and wavelength of the photon was. A couple of notes here. The energy must be in joules. Why? Because H, Planck's constant, which makes this equation work, was originally given in joules. If you look on the reference tables, it's listed as having units of joule seconds. So the energy must be in, where is it? The energy in this equation must be in joules. Now, a couple real quick things before we get to the examples. I'll just write this down real quick. H is Planck's constant. 6.63 times 10 to the negative 34th joules times seconds. So, we said that every element has its own unique set of energy levels. That means that each element, because it has its own energy levels, can emit a unique set of photons of different frequencies. This is extremely useful. Okay? Since all the energy level diagrams are different, all of these different sets of frequencies of photons that can be emitted are called emission spectra. So if an electron gets excited and goes up to higher energy levels. As it falls back down, it emits characteristic frequencies of light that we can use to identify that particular atom, what type of atom that is. We can use this to determine what types of elements are present in a sample. So this is used in a ton of diverse applications. So let's say you have like a rock sample. You can actually get these electrons from the rock sample excited and determine what types of materials are inside. Or what types of elements, I should say, make up the sample. So a geologist might use this idea of emission spectra. We can also we can use emission spectra to determine the composition of a star. Certain stars, different types of stars, have differing amounts of certain elements. So if we look at their emission spectra, if we look at the light that is coming to us from that star, then we can actually determine, based on what types of light are very bright, what types of light aren't as bright, what is helping to make up that star, what star is composed out of. And actually, this is also useful in a ton of different medical techniques. Okay, figuring out, like, especially what's in the body, what something is made out of. Okay, like let's say, you know, God forbid, there's like a tumor or something, or you need to get something imaged. This can help us. There's one other thing we have to talk about. We've talked about emission spectra. These are the types of light that are emitted by a certain element, and they're all different, so we can identify what elements are present. There's also such a thing called an absorption spectra. This occurs when white light is made up of all different types of frequencies, made up of all frequencies of light, or all colors, you could say, passes through what is known as an elemental gas, a gas made up of just one or a few types of elements. Those gases, as the light passes through them, some of that light will interact with the atoms in that gas. Some of those waves of light will excite electrons in those atoms. And when they excite the electrons, that means they'll go up to higher energy levels. It'll basically take that frequency of light out of the white light sample, and as the electron falls back down, it will either radiate a different type of light away, or it'll radiate the same type of light, but in a random direction. So imagine you've got white light coming towards you, but it's shining through a gas. Some of those colors that are combined in the white light are just taken out. So some of the frequencies get absorbed. And what this does, once the white light reaches us and we look at all the colors, it leaves dark spots. Okay? And leaving dark spots in the spectrum. Some of the colors haven't come through. Just like bright lines in an emission spectrum can help us determine what type of elements are present in a sample, dark spaces in an absorption spectrum help us determine the same thing, except in this case, it helps us determine what elements are present in that gas. I will show you examples in class of both emission spectrum and absorption spectra. So the key here, what I want you to take away from this video, is that we have talked about the history of the atom. We've refreshed our mind on what happens when electrons gain or lose energy, or what causes that. When they absorb a photon, they go up in energy level. When they emit a photon, they go down in energy level. And we talked about how that's different for all the different elements, and that can actually help us identify what types of elements are present in a sample. In the next video, we will go through the examples that show us how to calculate all these different energies and frequencies that occur when light and electrons interact.